Okay, welcome back to the class. So we continue with this example 6.3. So obtain the RTL design that realize the following computation blocks. So we have these two equations, x is equal to or assigned by this e multiplied by a plus b plus c, and we have y equal to a plus c multiplied by c plus d. And for the first question, design the data path that allow for concurrent computation of 3 addition. Do not perform code restructuring. This means that x is realized as it is, so no need to transform this yet in this question. So we need to design the data path of this. So try to do this so we can have this. Okay, so let's do the first one. So we have two equation where the first one is this. X is signed by e multiplied by a plus b plus c, and we have y is a plus c multiplied by c plus d. Okay, so what we need to do first, so we need to transfer this to what we call a DFG, design flow graph. So we have the equation already, so we can straight away design the DFG. So we can actually create the what we call the single assignment form, where we can have something like this. A1 is a plus b, a2 is a1 plus c, and we have x is actually e multiplied by a2. So this is the single assignment format assignment, and from this we can create the FG. And what about y? So for y we can do something like this, a plus c, so we can have a3 in this case, so we get a plus c, and we have c1 is c plus d, and we have y is actually a3 multiplied by c1, right? So this is the case. So from that we can create our DFG. So to create DFG, so we can have this, right? So we can have this is plus, and then we can have a plus b, this is a, this is b, and here should be a1, right? And you can have another operation which is add also, can be here, where this is a1, you add with c, and you can have a2, and after you, this is a2, and the last operation is this multiplication, multiply a2 multiplied by e, you will have your x here. So this is DFG for x. Now you can create the DFG for y based on this. All right. So you have a plus c, which is a3. So you can have another one here. And here is a. This is c. So plus you have a3. And you have another one, which is this one, which is c plus d, c, d, plus, and the output is c1. And the last one is this, where you have c1 and a1, you multiply, and you have y as the output. So this will be the FG for y, and this is for x. Yeah. So from this, we want to create the schedule and also allocation, so that we can have the RTL code later on, and of course after RTL we can have the data path. All right, so let's have this. See, all right, so we can have the cycle for each operation. So let's have something like this, where we need to refer to this, yeah, a plus b, and we need to remember that we are this, yeah, we are allowed to use concurrent computation of 3 addition. Means that in one clock cycle we can have up to 3 addition. And when we look at this, yeah, this 3 addition, we can do this in one clock cycle. Yeah, so we can have something like this, where we need to locate or transfer A to a register. So in this case, we can have up to 3 addition, right? So let's have, okay, so this is the first addition. So we can have this one, a plus b, we can have this. So we can do something like this. This is A, this is B, and we have the output here. But in scheduling and allocation, we need to allocate the resources to our design. So in this case, this we assign to a register. So in this example, I use dot, yeah, to represent a register. So no need to use a box, yeah, because it will make your drawing more complicated. So in this case, you can use a dot like this. So this one we call it or we assign to R1, all right, at the first cycle. So let's name this cycle as 0, and we transfer A to R1, yeah, and this one is R2, and this one we transfer B to R2, and we save the result of this operation in R1, right? A plus B, and save the data, the result in R1, all right, to represent this, yeah. Now our A1 is in R1, all right, and C, what about C, right? So we can have C in R3. We have another operation. Okay, we can have C in R3, yeah, where we have this is C, this is in R3, and this should be A, C plus A, this one, C plus A, and this is A actually, the same A. So we can just tap the data here from this and this, and we have the result in maybe we use R2, all right. Now we can use R2 already because here, yeah, B, we don't need B anymore in our design, all right. We don't need B anymore in our design, so we can reuse R2 register, yeah. B is done here, A1, and later on we don't need B anymore, so we can means that R2 is available after this operation, so we can save the data, right, A plus C here in R2. So all right, no need R4 register or any other register. So try to minimize the number of register that you use in the design. So in this case, because R2 is available now, so we can use R2 to store this the result of this operation. And one more is operation is this, yeah, C plus D, and of course our C is in R3 and D should be in another register, which is D here, and we can save this in R4, and this is plus R4. Why we not using as R3, right? This is because C, we want to use C here, so we need to preserve the value of C in R3, right? So in this case, instead of R3 here, we use R4, and this is of course R4, right? So now C is used in the next operation here, which is the this thing, this one, right? A1 plus again, so we have plus, so R3 now is still in R3, so we can bring this R3 to this is R3. Okay, so R3 is, now we want to do this, Okay, R1 here, this is A1 actually, remember, this is A1 and this is C. So, and this is plus, right? And we have, we can store in R1 and we can get this one, all right? And in the next one here, we can have the E, all right? But E is not in the register yet, right? E is not in the register yet, so we need to, in this case, we need to have E in here, E. So where to put E? So we need to look at which one is available. So R2 is not available yet, all right, because we want to use this one to multiply with this one here, and means that here R3 is available, right? So we can use R3 here in E. Multiply to get the result here, which is can be in R1, and this should be X, yeah. So this should be S1, this should be S2, this is S3, right? So we have X in this case, and for this one, this multiplied by this, so we have Y here, and we can use R2, right? Because R2 is available now, or you can use R4 as well, right? Either one. So in this case, I use R2. Okay, so so we can see that this is A1 based on this, and this is A2, yeah, and this is A3, this is A3, and this is C3, all right? So this we call the scheduling, where we can see that we schedule the operation here to different cycle. So this is cycle number 0, that is cycle number 1, cycle number 2, this is cycle number 3, where the first cycle we transfer the data, the input into R1, B here into R2, C into R3, D into R4. And the next cycle, we do this operation. We add this to get A1, and we store in R1. And also at the same time, and in the same cycle, we do this A plus C, all right, to get A3 and store in R2, and C plus D to get C3, and we store in R4. And S2, we do this A1 plus this C, A1 plus C, we have A2, and we store in R1. And the next cycle, and the same cycle S2, we transfer E to R3, and we multiply in the next cycle, multiply by R1 here, which is A2, and we get X. In this one, all right, we can here A3, C3, R2, R4, we multiply here, and we get Y, and we save in R2, right? So this is called scheduling, all right? And at the same time, we do the allocation, where we allocate the data to the register, all right, and also the operator that we use. Yeah, so in this case we use this allocate to R1, R2, and this we do this, and we save in this register and so on. This is called allocation. So from this we can create the RTL code. All right, so from this, now let's create the RTL code. So for the first cycle, you can see that what we do is actually this. First is we transfer A into R1. The next one is we transfer B into R2. And we transfer C into R3. And the last one is R4. We transfer D into R4. So this is the operation, or these are the operation that we do in the first cycle, or S0. And the next cycle, what we do is this, and this, and this 3 add operation. All right, and it's happened or performed at the same time or simultaneously. All right, so the first operation will be R1, where we add R1 and R2, and we stop at R1. All right, so let's name these as adder number 1, this is adder number 2, this is adder number 3, right? So because we have 3 adder now, so let's name that as this is adder number 1. All right, this is adder number 2, this is adder number 3. So means that the first operation we use adder number 1, and for this operation R2 we use adder number 2, which is R1 plus R3. This is adder number 2, and for this is R4, which is R3 plus R4. This is adder number 3. All right, so these are the operation that we do in S1. So the operation in S2 is this. Maybe we use the adder number 1 for this one, one adder only, right? So R1 is R1 plus R3, adder number 1, and we have R2, yeah, R2, R2, here is R2 multiplied by R4. And we have another operation here. We transfer E into R3. Right, so remember we have semicolon for the RTL code. And let's say we have another signal called y done to tell us that the operation of y is finished here. So activate this y done equal to 1 when this operation is finished, or the y is available here, right? And the last cycle, S3, we have only one operation, which is R1 is R1 plus multiplied by R3. Right, R1 multiplied by R3. And let's say we have another signal called x done equal to 1 when the operation is finished here, so that we know that x is available here, right? So this will be the RTL code for this. So from the RTL code, we can create the data path. All right, so let's have this so that we can draw our data path. So let's draw our data path here, but we need the RTL code in order to draw the data path. Okay, so from the RTL code, we can define the data path already actually. So here we can know how many register that we need. So in this case, we need R1, R2, R3, R4, right? There is no R5 or any other register. So we have 4 register. So let's draw 4 register. Okay, so we have 4 registers. So let's say this is register number 1. This is register number 2, number 3, and number 4 here. And this is R1, R2, R3, R4. And we have how many operation here? We have 3 adders, adder number 1, number 2, number 3, and we have 1 multiplier. So we have 3 adders and 1 multiplier for the computation. So let's have that. So maybe we have the first adder is here, the multiplier is here. We have 3 adders. So this is adder number 1, adder number 2, adder number 3, just like that. So this is multiplier. This is adder number 1, adder number 2, adder number 3. And now we need to do the connection. All right, how these registers are connected to this computation unit. All right, and again, it is based on the RTL code here. So let's look at the first R1. What is the input, or what are the inputs to R1? So we can look at here. So R1, we have here A to R1. Also, this from the adder number 1, the output should go to R1 also. And this is the same. This is adder number 1. Yeah. So and here we have another one, which is the multiplier. So we have 3 inputs for R1. And remember, yeah, because this is the register, only 1 input is allowed to enter the register at one time. So we have 3 waiting out here to enter 1 input here. So means that you need a multiplexer just before R1 to select which one to go into R1, all right, at one particular time. So in this case, let's have our multiplexer draw, maybe draw like this for multiplexer, use one line only. Yeah, this represent the multiplexer, right, to go into R1. So we have 3 input here. Okay, and this is from multiplier, from the adder number 1, and also from the outside A, right? So let's first we have the output from the multiplier. Okay, the multiplier is here. One is from multiplier. Another one is from adder. So this can be from adder. Okay, the input from the adder, and then the last one is input from A, right? So that is for R1. What about R2? So for R2, again, we need to look at the RTL code. So here is R2. One is from B. Another one is from adder number 2. And another one is from multiplier, right? And there is no other input to R2. So there are 3 to 1 also. So this is actually a 4 to 1 multiplexer, yeah, but we use only 3, right? Not 3 to 1 multiplexer. This is 4 to 1 multiplexer. And this one we need 4 to 1 multiplexer as well. So we have this. So again, we have the one is from multiplier, so we can actually get from here. This is from multiplier, so just have the connection like this, right? So means that this from this multiplier can go to R2 as well, right, for this one. And from this we can have number 2, so we can go maybe we move a little bit here. Right, so that we can have this from adder number 2 go to this here, right? So this is from adder number 2 go to R2, which is this one, adder number 2 go to R2, and the last one will be from this, from B. So you have B input here, right? So this is for R2, and for R3, so again we need to look at the RTL code. So where is R3? So we have C here for R3. We have E right? So that's it. There is no other input for R3 except these two, C and E. So again, we have 2 to 1 multiplexer here. First is C, the second one is D. Okay. And for R4, look at R4. So first one, C and not D, yeah, C and E. So this should be E. For R4, we have D and this. D and adder number 3, right? So we can have 2 to 1 multiplexer. And we can have this for D, and this is adder number 3. All right. For input to the R4. So done. So this should be the input to the register that we have. All right. So this is 4 to 1 mux, 4 to 1 mux, 2 to 1, 2 to 1. And what about the connection between the register and the output of the register and the input of the computation block? This, right? So again, we need to look at the RTL code. So for example, for this, yeah, adder number 1, or this one first, the multiplier. So multiplier, you have 2 operation here. First one is this. This one, and the second one is this one, right? So you will have input to the multiplier something like this. Yeah, if you look at this, this is R2 and R4, or we can write like this, R2 multiplied by R4, and also this one R1 multiplied by R3. All right. So you can have something like this. Means that this input here, right? You don't have not only one input but 2, right? And the other one input here, you have 2 input as well. So means that you need a multiplexer as well to select the R2 to go in the first input. So for example, if your multiplexer, your multiplier here, input A and B, all right, to go to A here, you need a multiplexer, and to go to B here, you need another multiplexer, because here at the input you need to select whether you want R2 multiplied by R4, R2 multiplied by R4, or R1 multiplied by R3. All right. So here again, we need a multiplier. So the first one, maybe we R1 R1 and R2. So we can have something like this, R1 and R2, and R3 and R4 for this one, right? So we can have here, R3, and we can have R4. For this multiplier should be done, right? Make it looks better. Okay, and what about this adder number 1? So again, we need to look at the RTL code. So if we look at RTL code here, adder number 1, so we have this is adder number 1, R1 and R2, R1 plus R2, R1 plus R2, and here R1 plus R3. Right? So this the same signal, so no need multiplexer. So you can straight away get from this R1, go straight away to one of the input of your adder, but because this one is R2 and R3, so you need a multiplexer. So again, here you need multiplexer, and one of the input is from R2 and another one is from R3, right? So this is R3, so you can tap from here. This is R3, right? And you can get from this. So this is R1, right? And here is can be R2 or R3, R2 or R3, right? That is for adder number 1. What about adder number 2? So the adder number 2 is this, and yeah, we only have one adder number 2, one operation here, so it should be easy. R1 plus R3, so we can get from R1 here, and another one is from R3, so we can get from here. So this is for adder number 2, very easy because we have one operation only, no need multiplexer. And the last one is adder number 3, and again adder number 3 we have only one operation here, R3 plus R4, so it should be easy. So we have R4 here, and we have R3 here. You can have R3, right? So this is the connection for this, the input and the output is done already, we have. So yes, so this is our data path unit, DU. And of course you need to have the signal here, all right, for the select signal. So let's here, right, let's name this as maybe SEL1, this is SEL2, this is SEL3, this is SEL4, and register, you need to have the load signal, so LD1, LD2, LD3, LD4, all right, for load signal. So of course, for example, for this multiplexer here, if you select 0, means that you select this from the multiplier. If you select 1 from the adder, and if you select number 2, this is from A, this is the same, 0, 1, 2, this is 0, 1, this is 0, 1, and this let's call this this is select M1, this is SEL M2, this is SEL adder, right? And you have 0, 1, 0, 1, 0, 1. Okay, so that are the signal that we need, yeah, for the DU. And this is the DU actually. And we can write the code, Verilog code or Verilog program to describe this DU. All right, later we will see how to write the Verilog code to describe this DU. Okay, so that will answer this question. All right, design the data purpose that allow concurrent computation of 3 addition. So we can see that we can have 3 addition here, 3 adder. All right, and this is the connection. All right, just like this one. All right, same thing. And of course we have this. Okay, so we start the design from the DFG, and we have the schedule and allocation, and also the RTL code, right? And we have the DU. And we will not stop here. Let's try to finish this, yeah, by writing the code for this, right? And also we try to create the CU control unit for this one also. All right, this is the additional example. So let's create the CU circuit for this one. So how to create the CU? So again, the CU is come from this, yeah, the number of cycle, all right, the schedule, and also from the RTL code, all right, because the RTL code will give us when the signal here, right, this signal should be activated. All right, for example, at cycle number 0, so we want to load A into ART1, so which signal we should activate? All right, so means that SEL1 should be equal to 2 and LD1 should be equal to 1, such that A here can be loaded to ART1. Okay, so let's do that. So to create the DU, actually we can have the block diagram of the DU already, CU already. And remember, CU is actually the finite state machine, and we will use more type finite state machine. So in this case, our DU is this. We have the state register, and we can have what we call the output logic, and we will have the this we call the next state logic. All right, so this is of course the state register. This is output logic that will generate the control sequence actually, which is this control vector. And this one is the next state logic. All right, and the connection between these 3 blocks, all right, is like this. So we have this is D flip-flops, right? So the connection is like this. Yeah, the output from the next state logic will be the input for this, and this is negative H triggered, and we have the output, we call it control vector. There are many. So this will be based on this. Yeah. So how many bits that we need for the CV? So this one is 2 bit. All right. SEL1 is 2 bit because this is 4 to 1 multiplexer. This is 2 bit. This is 2 bit. All right. So we have 4 signal here. All right. 2, 2, 4. This is 1 bit. 5, 6. LD1, 7, 8, 9, 10. 10 signal. 11, 12, 13. All right. So we need 13 bit for the control signal or control vector. So this is 13. Okay, and remember, for more state machine or even melee, you need to have feedback from the output of the register to the next state logic. Right? And now, how many bit is this? Right? Yeah. So this will depend on how many cycles that you have. So in this case, how many cycles? You have 4 cycles. S0, 1, 2, 3, 4. 4 cycles. So 4 cycles, you need at least 2 flip-flops. Or in other words, this is 2 bit. 2 bit. Of course, this is 2 bit. And let's name this as state. And this one as next state. Right, the signal here, the name is next state. This is state. And yes, this is the block diagram for the control unit, yeah, or CU. And this one is the data path. Now we can create the Verilog code for this one as well, but how to generate this control vector? So to do that, we need to look at the Verilog code as well. And maybe I have something like this using the Excel to write or to have the code. So I can have the name of all the signals. Yeah, these are the name of all the control signal based on this, right? And also let's use this one for better view, right? So this is the these are the name, and make it smaller. Okay, so that's this bit number 0, this is bit number 1, bit number 2. Okay, and we have until bit number 12, and here we write the RTL code. Okay, so we have our RTL code, and this one we have the cycle or state. Okay, so let's use this one. Okay, so this is the RTL code that we have based on this. So now for the first cycle, we want to do this. All right, so to do this, what we need to do is to look at the design here. So for example, we want to load A into R1. So what we need to have is that we need to make this select SEL1 to 10 or number 2, right? So this should be 10, and LD1 must be LD1 must be 1. Okay, so let's make this center, right? And this is A to R1. What about B to R2? So B to R2, again the same, SEL2 must be number 2 or 10, and LD2 must be 1. So this one is 1, 10, and LD2 must be 1. And here C to number 3, C is SEL3 must be 0, SEL3 must be 0, and LD3 must be 1, and the last operation is C D to R4. So D to R4, D is 0. So SEL4 should be 0, and LD4 should be equal to 1. All right, and the rest make it 0. Okay, so this should be the control signal that should be activated in cycles S0 in order to do these all operations. All right, and we can represent this into a hex number, all right, hexadecimal representation, where this will be F, and this will be 0, and this will be 4, and then this will be 1. Yeah, 12 bit. So 140F H. So this will be 140F H in hexadecimal. All right. So this number we will use in writing our Verilog code. Yeah. Now the second cycle, where we have 3 operations. Look at the first operation, R1 plus R2, using adder number 1, and the result is stored in R1. So if you look here, go to this, and LD1 must be 1 in order to enable this to go into R1. So this one should be 0, 0. So this one should be 0, 0. And for the operation R1 plus R2, so this is R1 already, so should be no problem. But R2, we need to select here. So SELA should be 0. SELA should be 0. All right, here should be 0 to select R2, and this one is R1 already, R1 plus R2, and of course LD1 must be equal to 1. All right, this will be the first operation. For the second operation, R2 from adder number 2 to R2, so it should be this line. So SEL2 must be number 1. Number 1 is 0, 1 for 2 bit, 0, 1. All right, 0, 1. And the operation R1 plus R3, do we need to do something here? R1 plus R3? No, because we don't have any select or any multiplexer here. So it's already R1 plus R3, so should be no problem here. All right, but LD2 must be 1, because we want to load the data into R2. And the last operation is for the R4, yeah, from the adder number 3. All right, so from adder number 3 to R4, so it should be this way, and SEL4 must be equal to 1. All right, SEL4 must be equal to 1. And anything here? No. All right, this is already R3 plus R4, and we have here, and of course LD4 must be equal to 1, and the rest here should be equal to 0. So here should be 0 0 and 0, and we have this in hexadecimal. So this should be D, and this should be 8, this should be 2, and this should be 0. So in hexadecimal should be 0, 2, 8, D hexadecimal for the so for the second cycle. So we have the first cycle, this should be our second cycle, and for the third cycle, or S2, we have 3 operations as well. Here the first one, at the number 1, go to R1, again at the number 1, go to R1, so should be this, yeah, 0 0. So this should be 0 0, and LD1 should be 1, but we have the R1 plus R3 here, so this one is already R1 but plus R3. So how to get R3 here? Here SELA must be 1. SELA must be 1 here, right? That's it. For R2, the second operation, R2 is from the multiplier. R2 is from the multiplier, so where is the line? So it should be 0 0 from the multiplier. So the select is 0 0, but the operation here R2 multiplied by R4. So this is the trick. So we want R2 to multiply by R4. So where is R2? So here is R2, and where is R4? Here is R4. So R4, as to get R4, so SELM1 must be 0. SELM1 must be 0. And here to get S2, R2, so here should be 1. SELM2 should be 1. All right, so that you get this. And also LD2 must be 1, because you want to load to R2, LD1 must be 1. And the last one is E to R3, so R3 LD3 must be 1. How to get E? SEL3 must be 0. SEL3, where is it? SEL3 must be 1, not 0. SEL3 must be 1 here. And here, any other operation? No, we don't have. So this should be 0, and this should be 0. So the last one this should be E, this should be 3, this should be 1 0. So 1 0 0 1 3 E H in the hex. All right, and we have the last one actually, S3. So for the last one, we will have this operation R1 multiplied by R3, and save the result in R1. So again, R1 LD1 must be 1, right? LD1 must be 1, and the multiplier, so this line, So it should be SEL1 is 0, 1 or number 1. So it should be 0, 1 and multiply R1 multiplied by R3. So 1 is should be R1. So this is R1. SELM2 must be 0. SELM2 must be 0. And multiply by R3. So 1 is from R3. So SELM1 must be 1. Must be 1. And that's it. There are no other operation. So let's make it 0, 0, 0, 0, 0. So here we have number 8, number 4, number 8, number 0. So in hexadecimal is 0, 8, 4, 8, H. Right? So this is our RTLCS table, right? We can name this as RTLCS control sequence table. All right, so we will use this sequence to create this CV, all right, based on the cycle or state in this case. Yeah, so if state as 0, so the output CV here must be this number, right, 13-bit. And if as 1, so this should be the output. In state 2, this should be the output, and state 3, this should be the output here. All right, so when your DU receive this signal, it will perform this operation and give you the result of X and Y, right? So this is the additional exercise for this one, although you don't have to do in this example, but I give you I show you how to get your DU, the data path, and also the CU, and also the control sequence. Later in the next video, I will show you how to write the code, to represent this data path and also the CU, the control unit, and it is will be based on this control sequence or control vector, right? So see you in the next video.